Ethers are the last reactive of the functional groups. The cleavage of CO bond in ethers takes place under drastic conditions with excess of hydrogen halides. The reaction of dialkyl ether gives two alkyl halide molecules. Cleavage of CO bond in ethers. Alkyl aryl ethers are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yields phenol and alkyl halide. In the following reaction here, phenol reacts with alkyl halide to form alkyl aryl ethers plus Rx, where R can be any aryl group and X can be any halide. Hydrogen iodide, hydrogen bromide. Cleavage of CO bonds in ethers. Ethers with two different alkyl groups are also cleaved in the same manner. For example, taking ROR dash plus reacting with any hydrogen halide results in the formation of aryl halide plus ROR-OH, which is an alcohol. The order of reactivity of hydrogen halides is as follows. That is, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive hydrogen chloride, respectively. The cleavage of ethers takes place with concentrated hydrogen iodide or hydrogen bromide at high temperatures. The reaction of an ether with concentrated hydrogen iodide starts with the protonation of ether molecule. The step 1 involves reaction of methoxyethane with hydrogen iodide to form isopropyloxynium plus iodide ion. The reaction takes place with HBr or HI because these reagents are sufficiently acidic. Step 2. Iodide is a good nucleophile. It attacks the least substituted carbon of the oxonium ion formed in the step 1 and displaces an alcohol molecule by SN2 mechanism. If you can see in this reaction, the I- attacks this less substituted carbon which is present here of the oxonium ion, and it replaces it using the SN2 mechanism to form alkyl iodide and alcohol. This is the transition state of this reaction. Thus, in the cleavage of mixed ethers with two different alkyl groups, the alcohol and alkyl iodide form depend on the nature of alkyl groups. In the step 2 itself, when primary or secondary alkyl groups are present, it is a lower alkyl group that forms alkyl iodide using the SN2 mechanism. Further, continuing to step 3, when the hydrogen iodide is in excess and the reaction is carried out at high temperature, ethanol reacts with another molecules of hydrogen iodide and is converted to ethyl iodide. Here, ethanol reacts with hydrogen iodide and replaces ethanol iodide to form ethanol iodide and I-. This reaction can be interconverted as follows and is in equilibrium always. And further, iodide reacts with ethanol to form ethyl iodide and water. However, when one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. That is, tertiary halide reaction with hydrogen iodide forms methanol and carbocation. It is because in step 2 of the reaction, the departure of leaving group creates a more stable carbocation and the reaction follows SN1 mechanism. In case of anisole, methyl phenyl oxonium ion formed by protonation of ether. The bond between OCH3 is weaker than the bond between OCH65 because the carbon of phenyl group is sp2 hybridized and there is a partial double bond character. Therefore, the attack by I- ion breaks OCH3 bond to form CH3I. Phenols do not react further to give halides because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to the halide. This is the sp2 hybridization of carbon in phenol. This is a nucleophilic substitution reaction due to the sp2 hybridized carbon.